Alright, time for another draftphysics.com, debatephysics.com also, but nobody to debate, really. I can't find any humans interested in the subject of how the universe works to talk through any of the elemental physics and how really simple it all can be. So the Wikipedia page on charge is where I guess I'll start, and then we'll get into electricity, and then we'll get into magnetism, and this will probably use up quite a few videos, I would imagine. It's a lot to these kind of subjects, a lot of phenomenon to talk about. So, prefacing that though, so I'll just offer the simple explanation. So, as I have pointed out, it's a really simple universe, just made out of force and matter, two elemental kinds of matter, two elemental kinds of force. And you really don't need anything else to make a simple diagram of the function. So charge, you would think an AI would have already answered this question and pointed out, oh yeah, there's only one simple way to do it. Gary's way. Yeah, just happens to be Gary's way. This is the simplest way, right? You're trying to create this circumstance where you have objects that are repelled by each other, sames repel, okay, and opposites attract. So, it's not that complicated a scenario, right? So these repel and the opposites do the, whatever. We'll just make lines, like that or something, for attracting. All right, and so it's a pretty simple, there's not much to it, but there's obviously something to it. And the simple truth is 2 plus 2 plus 2 physics works, that you have two kinds of matter. All you need now is two kinds of force that have an opposite reaction when they encounter a piece of matter. So the electron force hits a proton. Well, these should be the protons and these should be the electrons, let's say. Okay, just to be clear, these are electrons, the reds are the proton. I just try to use traditional assignment. So a proton force hits an electron, and all it does is it comes out of the electron changed, okay, to a electron force. And a electron force hits, and it either sticks and gives it momentum, but if it already has momentum in the opposite direction, it just reflects. So you either get stick and push, or you get a reflection. So those are the two interactions. It reflects or it pushes. And then, there's a third interaction where it changes color. So the opposite happens here. Obviously, a proton force hits, it comes out, an electron force, it comes out a proton force, and the same rule is the stick and push or reflect. And the reflection means that a piece of energy that was pushing, okay, also reflects. So when one reflects, the other reflects. Now that simple diagram creates a perfect duplicate of Maxwell's drawing of charge as basically radiators, okay, that are radiating something that has an opposite quality to it, okay. Now Maxwell drew it as lines going in and lines going out, but really it's both, it's just a pressure, and this force, blue, is invisible to the red thing, and the blue force is invisible to the red, and the red force is invisible to the blue thing. And the only force that this can get pushed by is a purple force, or blue, and the only force this can get pushed by is a red force. And so now you can see there's obvious room for them being smushed together, because this red one can't see a red force. If a red force is coming this way, it can't get to this. It's going to turn into a blue force. And likewise, if a blue force is coming this way, can't get to the blue thing because it's going to be turned into a red force. And so you're just going to end up, no energy on the inside, lots of energy on the outside. They're going to move together. And the opposite would happen in between them, is that the force would, if the two objects are moving towards, that's going to reflect because it's moving towards, and it would end up creating more and more reflections until it started sticking and causing momentum away from each other. So it explains attraction and repulsion in very few minutes, 3 minutes. What was it? 3 minutes. So a simple diagram. This is all you need to explain why there's attraction and repulsion and why electrons and protons behave the way they do. That's it. That's all you need. Two kinds of force moving the speed of light, two kinds of matter that collect the force, essentially, and two kinds of interactions. That's it. That's all you need. All right. So it certainly wins the Occam's razor award, and I would argue that it really doesn't have a flaw. It works as a diagram of charge. And it's frankly, it beats the hell out of their nonsense. So all the things they describe, I can say, oh, well, that's this. You know, it's the field, it's the energy in the universe. And, you know, the force tells the matter where it's going, and the matter changes how the force is going to reflect to the rest of the universe. It changes how the matter looks. All right, so electric charge, okay, symbols, is the physical property of matter that causes it to experience a force when placed in an electromagnetic field. So, you know, that's really, you know, causes it to experience a force. I mean, it doesn't really have much of a choice, I would argue. That the energy is already in the universe. The fields already exist, and all you can do is change what color they are. Okay. Electric charge can be positive or negative, so there's two properties, two polarizations. They could say north and south. They could say, you know, electron, proton. Like charges repel each other, unlike charges attract each other. So again, the simple answer duplicates that perfectly. An object with no net charge is referred to as electrically neutral. Now that's the net charge is the word, and net charge doesn't mean much, right? So I could put a proton and an electron could come together and stick together, and you'd say, okay, well, let's call that a neutron. But you know, it's not really neutral, right? If you spun it, it would look purple, right? If I spun blue and red, it would look purple. But you know, it isn't purple. You know, and if there's a far enough distance, I put this far enough away from you, it's going to turn purple. All right. Because something looks neutral doesn't mean it is neutral, in the sense that its appearance at different positions will be different. So again, if I had two of them and they were in proximity to each other, distance-wise, obviously this one is going to be a lot stronger because it's closer to you, right? So all I have to do is reverse it, and now all of a sudden this is much weaker. So all I have to do is have a polarized object, and I can create very strong. You know, so when you're closer to this, that's very powerful. But then as you get past that, then this gets strong. So it goes from being this, and it turns into this as I move into an atom, for example. The polarization changes. All right. Early knowledge of how charged substances interact is called classical electrodynamics. Well, whatever. This disgusting concept of separating physics into some sort of old and new, when it's either good ideas or bad ideas, frankly. And it's not about how old the idea is. And it's still accurate for problems that do not require consideration of quantum effects, whatever the vague category of quantum effects is. So, you know, fundamental theory in physics that describes the behavior of nature at below the scale of atoms. It is the foundation of all quantum physics. So quantum effects are the same as quantum mechanics, is the same as quantum physics. So just keep using the same word to define a word. Brilliant. Gravity causes gravity to be gravitational. Did you know that? Electric charge is a conserved property. So there's, you know, that's a sort of tricky language. It's obviously the idea is you can't destroy charges and you can't make them disappear, or you can't make them reverse. The net charge of an isolated system, the quantity of positive charge minus the amount of negative charge. Now the amount of charge is measured in these units of what the electron, they're like little suns, okay? They're little radiators. and they're going to radiate the universe that they're in terms of the force. And obviously the little protons are always going to be radiating red, and the electrons are always going to be radiating blue. Negative charge cannot change. Electric charge is carried by subatomic particles, so it doesn't carry it. It reacts to it, and it carries it as force, okay, when it's stuck to it. So it's going the speed of light until it hits an electron and pushes it. Now the force isn't going the speed of light anymore. And that's the cause of gravity, actually. In ordinary matter, negative charge is carried by electrons, so they produce what we call negative charge, okay, and positive charge is carried by protons, so they have the phenomenon of being positive in terms of their emissions. In the nuclei of atoms, if there are more electrons than protons in a piece of matter, it will have a negative charge, but depending on where you're looking at it from. So the nucleus has probably got, you know, electron, proton. It's got a bunch of different charges it's made out of. The net charge is the proton positive, because the neutrons are this and the extra protons make the nucleus positive, and then the outer rings of electrons restore the neutrality. Okay, but it's never perfectly neutral, and it depends on where you are. You know, if the atom's this way, or the atom's, you know, at some other angle, then this is visible. If it's this way, you can't even see the proton. So, you know, what the polarization of the atom is really depends on where you're looking at it from. All right. It's carried by the protons in the nucleus of atoms. There are more electrons than protons in a piece of matter. It will have a negative charge. So again, that's a net charge, but it doesn't mean that the atom isn't lopsided. That is, there's, you know, it could look red from this side, red from this side, and blue from up here, and blue from down here. Depends on the shape of the atom. If there are fewer, it will have a positive charge. If there are an equal number, it will be neutral. Charge is quantized, so obviously the electrons and protons are quantized, and they're producing an equal amount of the red and the blue stuff. Their strength of their effect is the same strength, indicating they must be the same size object, yet they can have different mass. Okay, so it could be argued that the protons are heavier, and therefore that's why they're stuck in the nucleus, is because they're harder to move. It comes in integer multiples of individual units called the elementary charge. All right, so that's basically the charge of an electron, a free electron, which is the smallest charge that can exist freely. Particles called quarks, so this is the made-up, starts to get into the made-up stuff. There's no real hard evidence that forces you to believe there's anything elementary to a proton, that you can actually break a proton and get quarks. And they're not durable. You can't put them in a bottle. They only last, if they existed, a millisecond. So they're just a speculated particle, not a real thing. Have smaller charges, multiples of 1/3 e. So they say it comes in quantized bits, and then they say, but no, we have 1/3 units. You know, it's just too ridiculous, right? They say it's conserved, it's quantized, and then they say, no, not really. But they are found only combined in particles that have a charge that is an integer multiple of e. So again, they're still arguing that, okay, these things exist, but they only exist when they're in a proton, and when they're not in a proton, somehow they don't have this charge. In the standard model, charge is absolutely conserved quantum number. The proton has a charge of plus e, the electron has a charge of minus e. So again, it does come in those clumps, but it also, you have to understand the context of the environment that the charge exists in. And it could be argued that atoms have different levels of energy in them, and therefore the amount of charge between the electrons and protons can be greater or lesser depending on their position in an atom. So that you get into energy levels of electrons. Electric charge produces electric fields. So again, the field exists. Okay, it's not produced by these objects. These objects are merely, they exist in this field of energy. A moving charge also produces a magnetic field. So it really doesn't have anything to do with moving. It just has to do with the fact that you're changing its position. So if you spun an atom and it had a positive and a dark side and a light side, a plus side and a minus side, and you spun it, you can understand that that movement isn't creating a change. This changing the polarization is what's causing something else that's looking at it that can see that change to keep trying to switch also. So it tries to match this pattern, and that's the induction. Okay, that's the magnetic field. All right, the interaction of electrical charges with electromagnetic field. So it's all this. There's only one field. That's this charge field. There's only charge, so there is no real electricity and there is no real magnetism. They're both just a consequence of the existence of this relationship between the force and the matter. All right. A combination of electric and 4 fundamental interactions in physics. So these 4 fundamental interactions are all nonsense. So, the strong force really doesn't exist. There's no strong force holding 2 protons together. So if I had another proton over here, another red marker, you could understand if I put an electron in between, I could get these 2 protons really close to each other, because essentially there's no force between them anymore. They can't see the red force coming off of each other because it's turned to blue. So you can understand you get 2 protons really close by just sticking an electron between them. Really simple solution. So there's no strong force. There's actually an incredibly weak force created by the electron mitigating, changing the force, making it inert to the protons, invisible to the protons. The SI-derived units of electric charge is the coulomb, named after French physicist Charles Auguste Coulomb, d Coulomb. In electrical engineering, it is also common to use ampere hour. It is. I never even heard of one. In physics and chemistry, it is common to use elementary charge as a unit. Chemistry also uses Faraday's constant, which is the charge of 1 mole of elementary charge. Whatever. So they call this overview. That ought to be interesting. Overview. All right, this overview is probably just going to be a reiteration of what they already just said. So, and it's going to be missing, there's the sort of a key point that has to be made is that, their model of an atom is all wrong. So, you really have to appreciate that they have made a terrible mess out of describing, and they went from bad to worse, right? It was already bad, okay, the Bohr model, and they went even further and made it even worse. So the solar system idea is just wrong. All right, so we know it's a positive in the center. You got extra protons, okay? Yes, it's the wrong color. Who cares? And then you have the electrons on the outside too. Because this is a net positive, the net negatives will hang around. And you could understand there would be a simple geometry between these electrons. These electrons hate each other. They're not swirling around, they're not orbiting, they're hating each other, okay? They're stuck in positions. And when an atom shares an electron, it literally shares the electron, okay? Here's the electron, it's going to share its position. And this one's going to have its electrons. And the fact is the electrons are going to always be sharing their pressure because they're loosely affiliated. So the next electron is going to have to be here. This one will have to be here. And there's going to be a fixed geometry, okay, for where the pressure could be, where they'd all be semi-equidistant in the sense of an equal amount of pressure between the electrons. And that's the ideal. But obviously inside it's going to be more pressure than on the outside, so it gets loose and loose because you're getting further and further from the positive. This has to see the positive to be attracted, okay, and it's repelled by these negatives. You can just sort of understand that's the tension that the electron is in. And the same tension is to the nucleus. The nucleus has hot spots on it where it's decidedly negative, you know, and so these electrons have to be where, you know, where the blue part is, and this one has to be where the blue part is, and this one has to be where the blue part is. So there's a real hard geometry, okay, and that's why there's only 100 possible atomic structures, is because the geometry is fixed. It's all hexagons or squares or however you want to look at it, but it's all needs to be geometrically symmetrical. This electron has to stay here because it can't get closer to these electrons. Even though it wants to get closer to this proton nucleus, it can't do it because these guys are in the way. And if I push these guys out a little bit, then this guy comes in. If this guy comes in, he's going to push these guys out a little bit. But the more you push them out, the closer they get to you. So it's all a rubber band. But that really needs to be understood, is their model is nonsense. First they had this stuff swirling around doing figure eights and all kinds of nonsense, and then they turned it into big giant orbs. You know, it's like telling you that Jupiter, you know, is not where Jupiter is, that somehow Jupiter's in all kinds of places and the average of where Jupiter is what we see. It's, you know, we're not seeing some average. Atoms aren't solar systems. They never they never had good cause to assume the solar system model. All right, so overview. Tired already. Charge is the fundamental property of matter that exhibits electrostatic attraction, so whatever that even means, or repulsion in the presence of other matter with charge. So this isn't even, you know, this is getting into what happens when you have an excess of electrons or an inadequate number of electrons in a system, and it moves to the surface. The imbalance, you create an imbalance, the imbalance always gets shoved to the outside. So charge ends up being a surface characteristic. Electric charge is a characteristic property of many subatomic particles. So again, this is, what are you talking about? Subatomic particles, it's just electrons and protons, that's it. So they move from talking about the effect of applying extra electrons, or having an insufficient number of electrons, and creating a charged surface of billions of atoms perhaps, and then they move back inside the atom again. I mean, just really, really poor logic there. Electric charge is a characteristic of probably many subatomic particles. The charges of freestanding particles are integer multiples of elementary charge. So it's exactly as I said, right? Same sentence as in the first paragraph. Why bother with that? We say that electric charge is quantized. So exactly the same crack. Michael Faraday in his electrolysis experiment was the first to note the discrete nature of electric charge. So a certain amount creates a certain amount of effect. So this is again just a momentum argument or some other argument about the fact that it's not magic. It's like it's a substance. Okay, it's like it's money. You have a certain amount of it. You can give it away. You can get more of it. That kind of thing. But it's always in some kind of coinage. Pennies is the smallest bit. All right. Robert Millikan oil drop experiment demonstrated this fact directly and measured the elementary charge. So this was the fact that he shot X-rays at dust, knocking electrons off or adding electrons. So either made, you know, the X-rays either added positive charge or subtracted, added negative charge or subtracted charge. And so he could randomly make something positive or negative. It has been discovered that one type of particle quarks, so that it's this whole thing, it has been discovered. There won't be any Millikan experiment. They won't show you that. So you can see the oil drop moving around. You can see that experiment, but you're not going to see this experiment. That one type of particle quarks have fractional charges of either minus 1/3 or plus 2/3. So that's all they say so. It's not physics you're going to see so. But it's believed they always occur in multiples of, believed by who and believed why. You know, these are fair questions. Believed by who and believed why. They always occur in multiples of integral charge. Freestanding quarks have never been observed. So again, what does that even mean? Freestanding. So there's no quark being observed. They're just assuming the existence of a quark. Something happens here, and then they see something happen over here, and they're arguing that quarks did something here. But they don't have any quarks. They don't have anything. They're just saying the gremlin did it. The quarklin. So just kind of bullshit. By convention, who likes those? The charge of an electron is negative, while the proton is positive. Charged particles whose charges have the same side repel one another. Particles whose charges have different signs attract. So again, they're going to argue as if there's different particles that have this phenomenon of charge, and there really isn't. So they just ought to say substances, okay, that is, charges behave by these rules, and objects that have an excess of electrons or an inadequacy of electrons also display these characteristics of attraction and repulsion. All right. Coulomb's law quantifies the electrostatic force between two particles by asserting, I can't see that, that the force is proportional to the product of their charges. Yeah. And inversely proportional to the square of the distance between them. So this is just implying that these things are spherical and symmetrical because they are doing the inverse square law. So there are three-dimensional objects, generally speaking, would be the argument. Now, I would say atoms don't have to be three-dimensional. They can be kind of like galaxies. They could be flat. You know, they just have an orientation in one dimension. They have pieces in one plane, like I would argue maybe hydrogen or something. The charge of an antiparticle, so they're bringing up antiparticles. There's no groundwork that establishes the existence of antiparticles. It's just another pile of like Einstein's crap that they throw in here. Like, we have to believe all this crap, or we're not going to understand any of these subjects, which is kind of nonsense. Electrodynamics explains 99%, okay, of the phenomenon. You don't need antiparticles. It's just kind of bullshit. It is bullshit. Equals that of the corresponding particle, but with opposite sign. You know. The electric charge of a microscopic object is the sum of the electric charges of the particles that it is made up of. Which obviously the charge has to be made up of something, right? So if you add more electrons, you're adding more charge. You subtract electrons, you're subtracting charge. And obviously it's really hard to add or subtract protons. So yes, we don't even talk about adding and subtracting protons because it's just about impossible to do that. This change is often small because matter is made of atoms, and atoms typically have equal numbers of protons and electrons. So, I mean, typically that's not even true. I mean, half the atoms in the periodic table don't have the same number of protons as electrons. In which case their charges cancel out, yielding a net charge of 0, thus making the atom neutral. So again, the atom is neutral if you spun it. But if you're looking at it, it's like spokes on a wheel. There's places where it's going to be more positive than places where it's going to be more negative. Depending on where you're looking at the atom from, it's going to look a different color. All right. It has a positive and negative. It's polarized. All right. An ion is an atom, or a group of atoms that has lost one or more electrons. Okay, so this is the part where you're saying, okay, well, what does that really mean? Well, it means it has more blue than red, all right, because it's not balanced anymore. And so there's more places where it's blue than it is red, or it's more places where it's red than it is blue, so it's uneven. All right, and so that also provides you the obvious opportunity to combine it with another atom, because it's either got an extra electron to give, or it's got a a hole, that somebody else's electron can fill, giving it a net positive charge, katon. We need that word for, I don't know. Or that has gained one more electron, giving it a net negative charge, anon. Those were Faraday's words, so I guess that's why they're using them. Monoatomic ions are formed from single atoms, while polyatomic ions are formed from two or more atoms that have been bonded together. So they're bound, but their exteriors are deficient. So they, and you have to understand that when two atoms are sharing an electron, one of them is obviously a negative ion and the other one's a positive ion, in the sense that if you rip it apart, one of them has to be the one who gets to keep the electron and the other one loses the electron. So you automatically create a even number of ions every time you split atoms that are combined, in each case yielding an ion with a positive or negative net charge. During the formation of microscopic objects, constituent atoms and ions usually combine to form structure composed of natural ionic compounds electrically bound to neutral atoms. The whole idea of sharing electrons happens. That's chemistry. Thus, microscopic objects tend towards being neutral overall, but microscopic objects are rarely perfectly net neutral. So why say it? Why say they tend to be neutral, but, well, no, they're not really neutral. They're only almost neutral. So just say they're almost always somewhere close to neutral, but not quite. And really, the only thing that makes them unneutral is the fact that they can't have that perfect symmetry, because they can't fill all three dimensions, unless they get really dense. Sometimes microscopic objects contain, you could say the same thing if you took little pieces of round, little styrofoam beads. You can't make a round ball out of them if you only use like 3 of them. You have to use kind of a lot of them before you can make a nice sphere out of them. Sometimes microscopic objects contain ions distributed throughout the material, rigidly bound in place, giving the overall net positive or negative charge to the object. So this is sort of like getting into crystals and the bonding points between, and how the fact is that the shape of a molecule matters. The proteins are long. They're going to be in rows. There's lots of things that you could understand, because the shape of the atoms requires there to be places where there's joining. There's joints versus the long bones. Also, microscopic objects made of conductive elements can more or less easily, depending on element, take on or give off electrons. So, depending on the material, like metals are really good at collecting charge. And other objects aren't so good at especially spreading it. So insulators, the charge doesn't migrate. So wherever you put the charge, it sort of stays. The electron stays in that place. The pressure can't be balanced. So it can't balance the pressure with all the other atoms. The pressure in difference stays where you place it. And then maintain the net negative or positive charge indefinitely. When the net electric charge of an object is non-zero and motionless, the phenomenon is known as static electricity. So the idea of whether or not it's motionless is, I don't think, is something you need to even bother thinking about, because obviously it could be doing a lot of moving around, but the density of the charge stays the same. This can easily be produced by rubbing two dissimilar materials together, such as rubbing amber and with fur or glass with silk. In this way, non-conductive materials can be charged to a significant degree. So PVC pipe, lots of things can be charged. So they ought to quit messing with the idea of amber and fur and glass and silk, and just talk about the fact that some materials give away electrons very well and some materials collect them very well. So if you rub certain materials that do those things well. Inversely, you can create a lot of charge because you can pull off a lot of electrons off something. It gives electrons away easily, and vice versa. All right, either positively or negatively, charge taken from one material is moved to another material, leaving the opposite charge of the same magnitude behind. So this is just moving electrons now. So they, instead of saying, they shouldn't be saying charge, they ought to just say these are electrons. Because that's what you're really moving. You're moving electrons. In theory, they're the only way you can create the charge pressure. So you can't just move the pressure. You have to move the pressure with the electron. The law of conservation of charge always applies. So again, it's conservation of electrons and protons. Giving the object from which is negative charge is taken positive charge of the same magnitude and vice versa. So again, it's just exchanging the element units of charge, which are the electron and the proton. So you add protons, you add charge, positive charge, you add electrons, you add negative charge. And obviously you can just remove electrons to make something net positive. All right, even when an object's net charge is 0, the charge can be distributed ununiformly in the object. So that's just a concession that these atomic structures aren't necessarily neutral in any real sense. They're dipoles, and the dipoles can be tripoles. Like you could have an atom that has 2 electrons that are close together here and 2 electrons that are far apart here. And you could argue that it's more negative this way than it is this way, because the electron is small compared to the size of the nucleus, in the sense it's close. So from your view, it's very small compared to the size of the proton. So again, it's just these kind of arguments. I can have 2 fingers and I can put 1 finger and hide the 2 fingers. So it just depends on how I see it, what I see, what I can see. So it is that real. Electrons and protons see each other. Okay, and then atoms, polarized atoms, see each other. They see changes in the pattern. All right. Okay, even in an object, a net charge 0, the charge can be distributed non-uniformly on the object. So again, it can have a net charge, but all the charge could be on the head of a pin. In such cases, the object is said to be polarized. So the argument would be that the simplest dipole is the neutron. And the fact is any time you have an arrangement of electrons and protons, you're going to have all kinds of poles involved. So you're going to have, and again with the atom, I was trying to get to the point that you could look at it and you could say it has 2 south poles this way, and it has 2 north poles this way and this way. So polarization doesn't have to be north-south. It can be at 45-degree angles, north-south. Atoms can be charged that way. All right. In such cases, the object is said to be polarized. The charge due to polarization is known as the bound charge. Well, whatever. That's just useless drivel. While the charge on the object produced by electrons gained or lost outside the object is called free charge. Bound charge would be, that's sort of like the idea of if you're sharing 2 electrons or 3 electrons between 2 atoms, then you can understand you're making strong ions if you separate them. And so there's a real deficiency in the actual number of electrons per nucleus. Because they're sharing so many of them, there's really a very small number of electrons balancing the overall number of positive in the nucleuses, because you're sharing more than 1 electron per atom. All right, while the charge on an object produced by electrons gained or lost from the outside is free charge. Okay, the motion of electrons is in conductive metals in a specific direction is known as electric circuit. So obviously Particular direction kind of is a silly thing to say when we know we can switch the direction millions of times a second. So why would you sit there and talk about direction? But anyway, the idea is it has to be moving. It doesn't have to move in one direction. It can just go back and forth, and that counts. Okay, as it's the same difference. Jumping side to side is essentially the same as running a mile. All right, unit would be terribly uninteresting, I believe, and history might be somewhat interesting, but you know, it's not really something I need to argue, I suppose. So maybe we'll take a pass now. Look how long it goes. Wow. So it's probably worth reading, so I'll just save it for another video though, and maybe I'll mix this up. So it's all going to be on one page: magnetism, electricity, and charge. And I will do what I can to annotate the videos in some way on the website so you know what the video has in it. But yeah, it is hard to take all of these subjects and do them in the right order, because all the phenomenons are based on understanding the nature of the electron and proton and the structure of an atom. And if you don't get that stuff right, it's all going to be a mess figuring out why all the rest of it happens. Mostly. I mean, it seems the appropriate thing now is to talk about how the polarization creates the effect of magnetism. And again, the magnetism is just, there's no force that a magnet's creating. It's just changing the way the force looks. So it's changing the arrangement of the red and the blue. It's creating a target with a blue center and then a white and then a blue and then a white, or a target with a red center and then a red and a red. You know, you can understand that these patterns are opposite patterns, and it's something has to match the patterns of the universe that are hitting it. And that's all that's really happening, is your pattern matching and such. Alright, so we'll call that a video. So yeah, we should remember that Wikipedia does suck. So let's conclude the video with the proper statement that these arrogant, obnoxious people won't even discuss the possibility that they have some of this wrong. That there's some error code. Won't even allow you to talk about it.